You changed one small row this morning, and your database wrote thousands of bytes to disk to record it. Not the bytes you handed over. Thousands. You paid for that in device where, in write bandwidth, you could have spent on something a customer notices, and in a few milliseconds of somebody's afternoon. Nobody tells you this, and no dashboard has a panel for it. So how much of what your storage layer writes is actually your data? Almost none of it, on most days. Divide the bytes that reached your device by the bytes you asked to store, and honestly, that is a number nobody on your team has measured. On a small update, that ratio lands between 10 times and 70 times. The grand term for that is write amplification, which is a lot of words for a division you can do in your head. Your money went on rewriting things you never touched, and your users paid a share of it too, in hours of their own patience spread thin across a year of small weights. You met that decision as a shrug in a configuration file. You picked a storage engine, or accepted whichever one your database shipped with, and you were done in 4 seconds. What you may not have noticed is how much that shrug bought, the cost of your writes, the cost of your reads, the way a delete behaves, and the shape of your worst answers. So what else did you agree to while you were not looking? Quite a lot, and you will meet most of it at 3 in the morning rather than in a benchmark. The slow answers you get blamed for, the disk filling faster than your data, the merge nobody knew was running, all of it traces back to that shrug, and all of it costs real money and real patience. You would think a database writes what you hand it and no more. It does nothing of the kind, and you will never quite trust a write again. The gap between what you sent and what the device swallowed is not a bug, and nobody is hiding it from you. You asked for it, quietly, by choosing where your rows live. Hold that question about your own data, since a measurement will settle it. What costs you today is arguing about which engine wins, and whoever won that argument. Somebody with different hardware always has contrary numbers. Speed is the wrong axis, and your bill was never one number. Here is the axis that pays you back. Where does the work go, and when does it arrive? No design makes work vanish, every design moves it. Your job, not your vendors, is knowing which resource just got more expensive and whether you can afford it in its new home. Cheap now and expensive later still shows up on your card. 2 families of design split the storage engines, and which one is under your data right now? One keeps a single sorted structure on disk and edits it where it lies. The other refuses to edit anything ever, and only adds new files. The name for the in-place family is the B tree, described by Rudolf Bayer and Edward McCreight in 1972, and it is the default in Postgres, in SQLite, and in InnoDB under MySQL. A page is the unit of reading and writing, 8 kilobytes in Postgres and 16 in InnoDB. Every page holds sorted keys and pointers to child pages, so the structure is a shallow sorted tree. How shallow is shallow? Fanout decides that. The term means the number of children one page can point at, and it is what makes the shape practical. The other family is called the log-structured merge tree, published by Patrick O'Neill and colleagues in 1996. That name sounds impressive, and it is really just shorthand for treating a disk as something to add to rather than to correct. It is the engine inside RocksDB, LevelDB, Cassandra, and HBase, and it is why MyRocks exists as the alternative to InnoDB. Why would anyone refuse to edit a file? The unit here is called a sorted run, one file of sorted keys, written in a single pass, never edited afterwards. The term for that property is immutable, which means exactly what it sounds like. A closed file is a permanent statement about what some keys were at one moment. So what do you do with a growing pile of such statements? Analogy, think of it as the difference between correcting a ledger in ink and adding a fresh line at the bottom. One keeps the book tidy and slow to amend. The other keeps the pen moving and leaves the tidying for later. Who tidies, and when? That is the part everybody forgets while the pen feels light. Start with the arithmetic, because it is the reason the B tree works at all. A page of 8 kilobytes, holding keys and pointers of roughly 16 bytes each, carries about 500 children. 500 per level gives you 500 keys, then 250,000, then 125 million, in 3 levels. So why is a lookup in a huge table 3-page reads rather than 30? That multiplication is why. Square the fanout and you have the depth. Now the write, and this is where it costs you. To change one row, the engine first reads the page your row lives on, changes your bytes in memory, then writes the whole page back. Your update was 120 bytes. The device received 8,192, because a page is the smallest thing it knows how to write. You amplified your own write by about 68 times, and the database considered that a normal Tuesday. Scattered placement is the second half of the bill. Writing sequentially is fast on a spinning disk because the head never moves, and fast on solid state because whole blocks are erased and programmed in one pass. Random writes fight both, since each one arrives wherever its key happens to sort, which is nowhere in particular. So what would you build if you were forbidden from ever writing to the same place twice? You would only add. A write lands in a sorted table held in memory, and nothing touches your data files at all. When that table passes a threshold, often tens of megabytes, the engine writes it out in one sequential pass as a sorted run, then starts a fresh table. The whole write path is one append to memory and, eventually, one long streaming write. A storage engine that refuses to store anything where it belongs is a wonderfully perverse way to go faster. Memory never survives a crash, and your colleague will ask about that first, so answer it first. Before the write enters memory, it is appended to a log on disk, a file the process only ever adds to at the end. If the machine dies, the engine replays that log and rebuilds the memory table exactly. Durability is real, and it costs one sequential append, the cheapest write any device sells. Immutable means what it says, so consider what happens to a key you wrote yesterday. Updating it never visits yesterday's file. The new value goes into memory, then into a new run, and now two files both claim to know that key. Two answers, one key, which sounds like a correctness bug. The fix is almost insultingly simple. Runs are ordered by age, newest first, and a reader takes the first answer it finds walking backwards from the newest source. Newest wins, and every older copy becomes harmless. Before I tell you what that trick costs, guess. You replaced a scattered 8 kilobyte page rewrite with a sequential append of your own bytes plus one log record, and nothing in physics hands you that for free. So which resource just got more expensive, and what happens next to the pile of runs you keep making? Say your answer out loud, then keep reading. Reads got more expensive, and your disk got fuller, because you now keep several copies of some keys spread across many files that nobody is allowed to edit. Tidying that up is called compaction. A background process reads several sorted runs at once, merges them into one, keeps only the newest version of each key, then deletes the inputs. Compaction is the deferred bill for every cheap append you enjoyed. But hang on. I called that append cheap a minute ago, and that is not the whole truth. The append is cheap, the write is not. Every byte you appended will then be read and rewritten by compaction, because that process keeps the pile of runs small. Measured figures commonly land between 10 and 30 times the bytes you handed over. You never avoided the work. You scheduled it, and it arrives a little after 3 in the morning. This is the part that catches people, and it catches them in production: deletion. In the in-place family, a delete clears space inside a page and the page is rewritten, smaller. In the append-only family, the engine never edits the file your key lives in, so a delete is itself a write. You append a marker saying this key is gone, and the name for that marker is a tombstone, because it marks a grave rather than emptying it. So your database cheerfully grew when you deleted things. Sit with that. Note, teams have deleted millions of rows and watched disk usage climb for an hour afterwards. Nothing was broken. The data leaves only when compaction reaches the tombstone and the older copy in the same merge, which might be minutes or might be days, since it first depends on how deep that old copy has already sunk. If a legal deadline is attached to your erasure path, this is the paragraph to write down. A postgres read is one walk, root, internal page, leaf, 3 or 4 page reads with a hard ceiling on the worst case. A log-structured read cannot stop at one place. It must consider the memory table and then every run that might hold your key, newest to oldest, until it finds one. The honest name for that is read amplification, the number of places you touch to answer once, and left alone it is the difference between 3 reads and 30. Did one path become several by accident? No. You bought that with the cheap write. In practice, nobody leaves it alone. Every sorted run keeps a small membership filter in memory, a Bloom filter, which cannot promise a key is present but can say definitely not with certainty, and that is enough to skip whole runs unopened. Each run also keeps a sparse index, one entry every few kilobytes, so a run that answers maybe does not cost you a scan. Read amplification is a limit you engineer around, not a verdict. Case in point, your colleague, reading over your shoulder, says the append only one is simply faster than. It is not, and the way to see that is to stop counting time and count space instead. A B tree deliberately leaves pages partly empty, filled to 70%, so one page has room for a new row without splitting in two. In practice, your data occupies roughly 1.5 times what a packed file would need, and that slack does not come free. The append-only family wastes space differently. Obsolete copies and tombstones sit on disk until compaction removes them. Your settled footprint is therefore your data plus whatever has not been tidied yet, commonly 10 to 20% above ideal. During a large merge it is worse, since compaction cannot run without room for its inputs and its output at the same moment. So which of those two wastes does your budget mind less? Notice that both families amplify writes, for opposite reasons, and that neither number appears anywhere in your query plan. Double the page size in the first and you double the bytes spent on one tiny update. Add a level to the second and you add roughly one more rewrite of everything passing through. The honest summary is that you cannot escape write amplification. You can only choose its shape, and choosing its shape is the only power on offer. And what does all of this do to the pager on your hip? Tail latency. Postgres gives you slow answers from page splits and from flushing dirty pages, mostly small and frequent ones. A log-structured store's slow answers come from compaction competing for the very device your queries are using, so your median read can look excellent while your 99th percentile read, the slowest one in 100, triples during a merge. The slow answer does not vanish. It moves, and predictability is the thing you traded away. Do not take my word for any of this, because you can check it yourself this week for the price of 1 hour. Take your smallest updatable row and update it in a loop for 10 minutes. Then read bytes written at the device, not at the database, since database counters cannot see what the device swallowed. Divide device bytes by the bytes you sent. If that ratio comes out close to 1, you are not measuring what you believe you are measuring. A ratio near your page size divided by your row size says you are paying for placement in the in-place family. A ratio that climbs over an hour and then settles says compaction has warmed up and you are in the other one. In practice we do not know what your number will be, and received wisdom is no guarantee here, since anybody who quotes a write amplification figure without your workload in front of them is inventing it. So which of the two wins? Neither. The real result of all this is not a winner, it is a dial with 3 ends, and you cannot pull all 3 at once: cheap reads, cheap writes, small footprint. Pick 2 and pay for the third. RocksDB exposes the dial directly in its level sizes and its compaction style, which is unusually honest of a piece of software. InnoDB hides the dial and picks defaults that suit most people, which is unusually kind. Neither one is cheating you. Which suggests a way to choose that has little to do with benchmarks. If your traffic is mostly reads of individual keys with occasional updates, and your worst answer has to stay predictable, the in-place family asks less of you. If you take a fire hose of writes and can tolerate a moving tail, the append-only family costs you less deviceware for identical work. MyRocks exists inside Facebook for that reason, and Bigtable made the same trade-off decades earlier. Which brings us back to the question at the top, about how much of what your storage layer writes is really yours. The answer is a small fraction, and its size was set by a decision about the write path, not the read path. In place means your unit of writing is a page, so a small update cannot avoid becoming a large write in the wrong spot. Append only means your unit is your own bytes, and in practice the trade-off is the whole of it. Two things to sit with afterwards, because the honest limits here are operational rather than theoretical. If a legal deadline is attached to your delete path, do you know how long a deleted row really survives inside your engine? And if a background merge started on your busiest node right now, would anything in your monitoring tell you, or would you learn about it from a queue depth 10 minutes later? You need not change engines this quarter, and probably should not. You need to know which bill you signed. Measure the ratio on your own workload, find out what your storage layer really does with a delete, then ask yourself whether the shape of that cost fits the shape of your traffic. If it does not fit, the dial was always there, and turning it is your call.